Welcome to the gases unit. This is the next unit in our New York State Regents Chemistry Curriculum. It deals with the behavior of gases and how changing certain factors will affect other factors of a sample of gas. So let's get started, and we'll kind of just dive right in. We'll take it step by step at first, and then we'll get into a little bit of math as we go. So, excuse me. A gas law is defined as changes in temperature, pressure, and volume, and how all of those will be affecting each other and how they're going to affect the behavior of the gas. So what you really want to be able to do to make this a lot easier for these three factors is understand or remember what they mean to the particles. So for temperature, we want to be thinking about the speed of the molecules. You know, temperature goes up, the molecules move faster. Temperature goes down, the molecules move slower. Pressure is a force. It's a force. And it's a force exerted by the molecules and on the molecules. So it's, a light force would be a molecule that hits the wall of a container lightly. A large force would be a particle that hits the side of a container with a lot of power behind it. And volume is space. So we're seeing how space, force, and speed all affect one another. Okay, so pressure is kind of new to this channel. If you're watching this in a string from the beginning, or, if you're just kind of getting stuck in one way or the other, we can measure pressure for Regents chemistry in two different ways. The first unit could be ATM, which is an atmosphere. The second way is something called a kilopascal, which is kPa. They both measure pressure, right? So it's kind of like how grams measure mass and pounds measure mass, or liters and ounces both measure volume. Okay, so they're two different scales, but they both measure pressure. Now, there are three individual laws that we're going to cover in this video today. And the first one is Charles' law. Charles' law is the law which we're comparing how temperature and volume affect one another. So for this law, what we do is we hold pressure constant. We ignore it. We pretend like it's not there, and because it's not going to change. So what we're really looking at with temperature and volume is we're seeing how does speed affect the space of a gas. And what we're going to find out is that this is a direct relationship. Anytime temperature goes up, volume of a gas goes up. Anytime the volume of a gas goes down, the temperature of that gas goes down. And I think it makes sense when you see this picture. In this picture, what we have are two different temperatures, a low temperature and a high temperature. And even though it's not drawn in here, you have to imagine that these molecules are moving faster than these molecules. And you have to imagine it, but it is a reality. Okay? The hotter these molecules are, the faster they go. And what they do, because they are moving so fast, is they expand and they get as far away from each other as possible. This takes the volume from being low to being high. A direct relationship between the speed of the molecules and the space that they occupy. Now over here on the right, what we know in direct proportions is that we can write this as V over T. And if V over T is a constant, then we could say V1 over T1 equals V2 over T2. And we could even plug in some, numbers to explain that. Let's say the temperature here is 300 Kelvin, and the temperature over here is 600 Kelvin. And if the initial starting volume was 2 liters, then what would my new volume be? And we could take these numbers and we could plug them into this formula by saying V1 over T1 equals V2, which is X right now. I don't know what my new volume is going to be, but my new temperature is going to be 600 K. And we do some cross multiplying and dividing, do this times this times this, and divide. And what we find out is X equals 4 liters. So the volume doubled when the temperature doubled. The reason this happens is because the increased temperature means the gas particles have more kinetic energy. They move more. And then they just naturally expand. Now, this is Charles's law. It holds pressure constant, changes temperature, changes volume. We'll move on to Boyle's law. Boyle's law is a little bit more maybe understandable without having to know what the molecules do. And what it says is that volume is inversely proportional to pressure if we hold temperature constant. If you take a balloon, right, and you take a balloon and you add pressure to it. Now, in this picture, it's showing a balloon if you were going to bring it down underwater with you. As you go down, the pressure starts to increase and the volume of the balloon starts to decrease. Because in these balloons, right, we are over time, or not over time, excuse me, over the distance, we are taking a small amount of pressure and doubling it, and then tripling it, and then quadrupling it. And as this force continues to get exerted on gas, it pushes the particles closer together. So this inverse relationship between pressure and volume looks like that. Graphically, it looks like that. Because as pressure increases, volume then decreases. In this movable piston example that we have right here, you see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 gas particles. They have 2 arrows of pressure, and therefore they set themselves at this particular volume, whatever that happens to be. When we add more pressure by adding more arrows, the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 same gas particles just have to get forced closer together. And because they're getting forced closer together, the space that they take up decreases. So when pressure increases, your gas particles are you're just pushing them close together. And on the flip side of it, if the volume is increasing, that's because the gas particles aren't colliding. They don't have as much force. This constant right here is the constant that you would need to do math for this question. The last individual law is called Lusak's law. And this is where we are looking at temperature, speed, and pressure, force. And I think it's kind of, I ask my students all of the time. I say, would you rather walk into a wall or run full speed into a wall? And the overwhelming majority will say, well, I'd rather not hit the wall at all, but if I had to, I'd prefer to walk. And I say, why? Why would you rather walk into the wall? And they say, it would hurt less. And it's kind of the exact same idea here. The faster a particle moves, the more force it's going to have. The slower a particle moves, the less force it's going to have. And so this is a direct proportion. When one goes up, the other goes up. When one goes down, the other goes down. If the particles move faster, the force will be greater. And because this is a direct proportion, we set it up like a fraction again, allowing us to go P1 over T1, P2 over T2. The picture shows the tails, slow-moving molecules, ice bath, right? So cold, ice bath, slow-moving molecules, pressure of 1.00. Not a lot of force. I mean, this force is actually equal to 1 atmospheric force, but it's low compared to these fast, super speedy, bigger molecules, because the faster these molecules move, the more pressure, the more force that they are going to start exerting on the inside of the container. And so when temperature goes up, pressure goes up. Why? All has to do with the speed. And when the speed gets greater, the force is increased. It's increased in both magnitude, but also increased in frequency. And so that's the introduction to our gases unit. Right? It covers the 3 laws that we're going to be learning about or diving deeper into: Charles's law, Boyle's law, and Lusak's law. And in the coming lessons, we're going to look at the combined gas law, which takes all 3 of these and puts them into one formula. So we'll take a look at that in the next video. I hope you enjoyed the video. Please make sure to like it, subscribe, and I will catch you in the next video.